In this lecture, we will have an overview of HVAC control systems, and in the modern day it is quite common that any large air conditioning system will have a sophisticated control system, and we are only going to just have an overview of the elements of a control system, and then we will look at some elaboration of the various concepts that are to be applied when we develop a HVAC refrigeration system. An HVAC control system, which may be a very simple system like a thermostat, or a much more complex computerized control system, will have four basic elements. It will have sensors, controllers, control devices, and there must be some source of energy for the control system. If you look at this block diagram, that shows those components of a HVAC control system. For example, the process that we are interested in is room heating, and by using a temperature sensor we can look at the temperature of the room, and what we will do, we will have a desired value which is known as the set point. So let's say we want a temperature inside the room to be 24 degrees C. It is possible that at some time the temperature starts to increase or it drops down, and based on those sorts of variations we want to have a control system that will allow us to maintain that temperature in the room. So what will happen there, the sensor will sense the temperature in the room, and it will send a signal to a comparison device. The comparison device will compare the desired set point value with the value that the sensor has provided, and that will generate a signal. Depending on the difference between the two values, an error signal will be generated, which will be sent to the controller, and then the controller, based on the error signal, will cause an actuator to move. So for example, if the temperature drops, then what will happen? The sensor sends a signal to the comparator, and it produces an error signal, and the controller causes the actuator to, for example, increase the rate of the air that is being supplied to the room, and that will again bring up the room temperature to the desired level. And it would be the other way around. If the temperature increases beyond the set point value, we want to reduce the airflow into the room by the same process, and that is how this basic control mechanism would be able to maintain the desired conditions in the controlled space, that is your room. The sensor will as I said, will measure the controlled variable, which could be temperature, or it may be humidity, or the flow rate. So we can have two types of sensors: analog sensors, which produce a continuous change signal according to the variable which is continuously or may be continuously changing. So it will produce a changing signal as well. Or you can have digital sensors, which provides signals which are discrete, that is on, off, or 0, 1. So those are digital sensors. And in an HVAC system, the typical sensors we come across are temperature measuring devices, humidity measurement devices, pressure, volume, flow rate, air velocity, and also liquid level measuring devices. So these are some common types of sensors you will come across when we look at a HVAC system. The controller functions to receive the inputs from the sensor. It processes the input, and produces that intelligent input signal for the control device. So the output of the controller would be an intelligent signal that will then accordingly control cause the control device to operate. The control device will definitely, as the name implies, will control the variable. So the control device may be a control valve, it could be a damper, it could be the coils for heating and cooling. That means we are controlling the flow rate. It can also control the speed of fans or pumps. So you can have these typical devices or components which are controlled in an HVAC system. The source of energy, we need a source to power the control system, and they can be the sources of energy that can be either pneumatic or electrical power supply. Now in a modern HVAC control system, the control system should fulfill certain objectives, and one of the principal factors is now the energy consumption. So lower energy cost and lower operations cost to have increased flexibility, and definitely assuring the quality inside the conditioned environment. These all objectives are fulfilled by using a proper HVAC system. There are a number of different types of control systems, and we will look at 5 different types and try to bring out the basic differences between these 5 types. One is known as the direct acting type, and that is the simplest type. So you will have a sensing element which will transmit power to a valve or a bellows or a diaphragm through some capillary, and it derives the energy from the process that it is actually trying to control. So we do not have an additional source of power. And a typical example of this is the thermostatic expansion valve, which you have studied, that increase in the superheat at the evaporator outlet causes the refrigerant charge in the sensing bulb of the thermostatic expansion valve causes an increase in the pressure, which is transmitted to the diaphragm, and that diaphragm then causes the movement of the needle arrangement inside the body of the thermostatic expansion valve, causing an increased flow of the refrigerant to the evaporator, and it will work the other way around when the degree of superheat decreases. The second one is an electronic or electrical system, and a simple block diagram of such a system is shown over here. You again have the controller, and we have the sensors, and you will have the actuator. So we have the inputs into the controller. So let's say in this particular case you have the outdoor air temperature, and you also have a sensor for the hot water temperature, and we have a set point over here. So for example, if the air outside, that outside temperature goes down, let's say we are talking about heating, so we are supplying hot water to the heating coil, and air is then passes over that heating coil to be warmed up, and then it will be sent to the room or the conditioned space. So if the outdoor temperature drops, it means there will be a greater heat loss from the conditioned space, and you will need to increase the temperature of the air. And what we can do, that will be done by increasing the supply of the hot water through the heating coil. So these two temperatures, the hot water supply temperature and the outdoor air temperature, so if you have a certain set point and the outdoor temperature drops below that, then what the controller will send a signal to the actuator, and where you have the control device, which is a valve, and that valve will then be allowed to provide a larger flow rate of hot water to the heating coil. So that valve will be operated through an electrical signal, and this is just a simple example of a electric or electronic system. A very common simple electrically operated device is the thermostat, which we find in our domestic refrigerators and air conditioners. But we can also have more complex elements of the HVAC system, which are operated by using electric or electronic control system, and these include solenoid valves, which can serve multiple purposes. They can energize oil burners, or as we looked at, it can increase or decrease the flow rates of the water through various circuits, and it can also control the electric heating if there is any, and they can also operate dampers, and they can turn on fans, pumps and devices like that. An electronic control system can also have a digital readout, and these days it is quite common to have control systems with visual displays. The third type is a pneumatic system, and historically that has enjoyed quite a large or diversified use in HVAC systems. And when we talk about pneumatic systems, we are using a compressed gas, and that is air, and that can be controlled. The pressure of the air can be controlled by the devices that we are looking at, like thermostats and humidistats. So those signals from the thermostats and humidistats will then be used to change the input pressure. And then the device that we are operating will be operated, and they have been again used for various purposes, that is opening valves or dampers and energizing other equipment. So this is again a block diagram of a pneumatically controlled system, in which the compressed air then causes the actuator to function, and then it operates the valve or a damper. The principal advantages of pneumatic air is that, of course, the air is cheap, and it's very durable and safe, especially in hazardous areas where you do not want any possibility of electrical sparks. And it is also capable of modulation, that is, with variation of the variable that you want to control, the compressed air's pressure can also be varied, and that will be quite useful for modulating various components. For example, like a damper, if you are, for example, using a 24-volt electrical control system, that will only have an on and off requirement for the damper. But if you want the damper to be open at intermediate positions, you can use pneumatic controls, and we can have the damper open at various intermediate positions. So this allows greater flexibility in your system, and it provides greater matching with the supply and with the load. Of course, pneumatic systems require that the air that you are using must be processed in the sense that it should be clean and dry and oil free, both as the control medium signal and to drive the various valves which use diaphragms. Next we come to microprocessor systems, and the most commonly used control system in modern day applications is the direct digital control or DDC system, and it requires microprocessors, as the name implies, for handling various inputs and generating a number of outputs, which can then control several different devices at the same time. And we again have a block diagram over here of a DDC control system. You have the conditioned space, you will have various sensors, they will be sending signals to the controller or the controller panel. You will have a user or the operator and machine interface as well, in the form of a display and sort of a keypad alongside. The principal difference between the DDC system and an electronic system is in the handling of the input signals. In electronic control systems, the analog sensor signal is amplified and then compared with the set point, and then we operate the desired component. Whereas in a microprocessor based system, the sensor input is converted to a digital form, and then we have discrete intelligent instructions in the form of algorithms which process the data and generate the desired output. And because these algorithms are quite sophisticated algorithms, we are able to control a very large system and in a very efficient manner. So you can have multiple buildings having a central DDC control system, and that with increasing complexity, the DDC control systems also have the capability to handle that complexity and also fulfill the desired basic objectives of a HVAC control system. And finally, we can also have mixed systems, in which you have a combination of controlled devices. So you can have electronic controllers which modulate a pneumatic actuator, and you can have also proportional controllers which are used by pneumatic actuators. So that is also a possibility. We will now look at a video in which you will be introduced to the historic development of various control systems and some more details about the modern day control systems and their elements.
So as we talked about in our overview on control systems, the controllers, the control devices in these systems really run the show. So we talked about how sensor signals get input into the controller, so variables like temperature, pressure, status from transducers, and that those controllers will take that input reading as feedback, drive them into control loops, and then output some signal, either analog or binary or digital, to control our systems. So we're going to look very briefly at how those systems have changed over time, but understanding that that input-output nature has really been constant throughout. So the control infrastructure has changed over time. So for the most part, we're going to see more of what's shown on the right here than we will on the left. So they're still out there. Let's give a little basic synopsis. So this pneumatic control is the older style of control that we had before digital, before electronic, before electrical. So what we have is these pneumatic controllers that are probably in a control cabinet or near some piece of equipment like an air handler. And these controllers or receivers have knobs so that you can adjust the control response associated with different elements in your system. So the problem here, because it's not all bad, I think a lot of maintenance folks would say that it's less black boxy than some of our digital controllers, where once you understand how these systems work, what you see is what you get. And you have all the knobs right at your disposal so you can adjust the system to stage it and adjust the control how you need to. But it is subject to a lot of extra maintenance with the compressed air systems, with the air dryers associated at the discharge of that compressed air, and then you gotta constantly maintain leak or have some type of leak detection program in your system, as that will not only use more energy to keep cycling those air compressors, but will start affecting your ability to maintain your sequences of operation. So with electric control, with these simple kind of modules we see here, we went from something like a 0 to 15 PSIG control signal to now we're using electrical wiring to accomplish those same input-output signals. So in some cases where we have a simple system, this may be a good application, because like pneumatics, there's a lot of what you see is what you get here. And you can have some limited interface, some adjusting of set points you can have here, so for individual control loops, this may be a good fit. However, these types of systems aren't able to be tied into other controllers or be brought into a front-end system very easily. For that, you need something like this digital control. So direct digital control, or DDC controllers, have that same electric input-output, but now we have this microprocessor-based device that can be interfaced with and have the sequence of operation either reprogrammed or reconfigured to have a lot more freedom and flexibility in how our systems run. Those devices can also be linked up to other devices through some specific protocol, and up to something like a UMCS front end for advanced facility management operation. So that's the control devices themselves, but how do they control? So we're going to real briefly cover a couple examples about the type of control that we see in our system. And the simple one is this on-off, or two-position control. So what happens here, and you can think about something like a residential furnace, so some heating system in your house, probably comes on when you cross some set point that you've given it, and it probably has some differential so it's not constantly cycling on and off. So it'll turn on at one point, it'll turn off at the set point plus the differential. So common and very basic systems and some of our zone systems. So one step of complexity beyond that is this floating control. So we're still dealing in binary outputs where we're telling something to go on or off. But now we've introduced a deadband. So with this deadband, we're adding some stability to our system by giving it a range in which it's told to hold its last value or float at that particular set point. So if you think about systems where you have some quick acting nature to them, like a pressure change, it may be beneficial to have a floating range or a deadband in which you're telling your system, everything's fine, don't make any control change until you get outside this deadband. But for most of our control loops in modern systems, we need to be somewhat familiar with this PID control, also known as PID loops. So this is most common in a lot of our digital control systems. We'll look at a couple systems specifically in the follow-on videos, but here we're going to give an overview for what the different components are of PID and what those look like from a control response standpoint. So you might hear that these controllers or control loops are able to be tuned. So what does that mean, and why might we want to tune a PID loop? Well, there's different elements, as we'll see, within a PID loop, and tuning those individually will change the control response that we have. It can make it more robust, faster, or less prone to instability. And the reason that we need to tune that is because each control loop is really specific to the process variables in place, to the different feedback lags that we may have, and even though we may see advertised controllers that are factory tuned, that we really need to be able to tune the system to the specific application and distribution and infrastructure that it belongs to. So what type of tuning issues might we see? Well, there's a couple that we could visually represent here. So the first one is this perpetual error. So when you're using a simplistic PID loop style, you might have a response as you have some, what we might call a step change, which we can think of as my system's been off, all of a sudden now my system is on and I want it to meet this set point. So I've just introduced this instantaneous error that I want my control loop to be able to tell some piece of equipment like a valve or a damper or a motor how much to ramp up to reduce that error. And here we can see we might have some response but it leaves us with some air at the end that doesn't go away. We can have what might be called an overdamp response. Maybe we've limited that steady state air, but we have such a slow acting loop that we may want to tune it so it has a more of a quick acting or more of a robust front end to it. We can have a quicker control loop, but maybe now we're overshooting a little bit. And in systems where we're susceptible to, say, high pressure temperature changes, like within a duct, that may become an issue. We may damage equipment. And we may have what's called hunting or cycling. So if you can ever imagine looking at something like an economizer damper, where it appears that damper is just closing, opening, and by the time it realizes it's overshot one end of the set point, it's shooting back to the other one. We would call that hunting, and that's something that tuning can address. So there's 3 settings as part of a PID loop that we could tune. So what gives it the name PID loop is this PID, proportional, integral, derivative. And the proportional response is based on the amount or magnitude of error. So it'll respond not constant, but linearly based on the amount of error that it sees. The integral component accounts for the duration of error. So it's integrating or accumulating all of the error that it's seen and adjusting its response accordingly. And finally, the derivative accounts for the rate of error. So it's almost projecting out and seeing, based on the change of error, what type of magnitude change it should have in its response to accomplish the set point. So another way to look at this is that we have with proportional a response that cares about the error right now. With integral, we're concerned with the past error, and with derivative, we're looking at the future error. So while we could tune these different settings in a typical PID control loop, in HVAC we're really just worried about PI, and we'll see why in a few minutes, but essentially P and I is enough with our slow-acting HVAC control loops, and because we have a fair amount of tolerance with things like error and response and how long that takes, that the D end of things can sometimes be more trouble than it's worth. So let's look at a couple examples here. So this in the general sense is what a control loop might look like. So from a control theory standpoint, this is what could be applied to different things in HVAC and other control applications. So essentially we have a set put that's going into a PID loop or a PID controller, and that's being compared to a feedback loop. So in a closed loop setting like this, you have some sensor that's bringing in the variable that you care about, an actual reading there, to the PID loop controller so it can make that comparison and calculate what the error is or the difference between the sensor input and the set point. Based on that delta, and depending on what type of settings you have in play between the PI and D, there's going to be a very specific output from the controller to a process that may change moment to moment. And that process is going to be where you make the change that affects the variable that you'd like. There may be disturbances and noises in your process and sensor input, but this is essentially what we have to work with. And we can think of that as a simple example with something like driving a car. So if you want to go into the next lane, your brain has become the PID controller. Your eyes are now the sensor input, and your hands on the wheel are essentially the actuator in this. Now your brain is automatically resetting these types of PI and D, because you know that if you make a small change with your hands, your brain may understand that you need to make more of a change, but it's trying to prevent overshoot. And there's different feedbacks associated with that process of changing the wheel, so you can change the position of the car, which is the process variable or what you really care about, and dealing with things like crosswind and glare. So using that feedback to make those moment-to-moment corrections in how much output you have. That's what this PID loop would look like for driving a car. And if you've ever had the fun experience of trying to sail a boat, you can understand more dramatically what this kind of feedback looks like. When you slow it down and you have a lot more lags like you might have in an HVAC system, you can see that you need to be very careful about what those settings are. How quickly you respond to something, how much you correct versus not getting the type of magnitude you want over time. And we can see that in our HVAC applications as well. So let's look at a simple coil or a coil discharge control loop application. So say we have a cooling coil, right? And we want to discharge so that we have a specific temperature right at the outlet of that coil on the air side in the duct. So we have a set point we're telling the controller that we want to keep to, say 55 degrees. And in the duct, right at the discharge of the coil, we have a temperature sensor that's bringing back what more or less the actual temperature is in that duct. So the process variable that we care about. So what we're trying to do is output something from the controller based on that error that's going to give a new valve position for the cooling coil. So the valve that controls how much water, how much chilled water goes through that coil, that valve position is going to be dictated by the output of that PID loop. So hopefully that valve position change affects a change in the coil discharge temperature that's picked up by that sensor, and then you're moment to moment making these changes to try to maintain that set point of, say, 55. We have some disturbances like airflow fluctuations, but really I think what's going to get folks here is the sensor itself and that feedback loop. So if you don't have a sensor in a good spot, if you have a lot of feedback associated or a lot of time that it takes for that sensor to see the right temperature and deliver that to the control loop, or if you have a very inaccurate or poorly located sensor, that's all going to play into how well this PID loop operates. So again, for this HVAC coil application, the proportional component, the way it's tuned, is going to compare about how much you're deviating from set point at a specific moment. The integral portion is going to care about how long you haven't been able to make your set points and adjust accordingly. And the derivative portion is something that we really don't even want to mess with because it's not worth it here, and it could overcomplicate or possibly cause some instability in our control loop. So more on proportional control. So this proportional or P control is, remember, proportional to the error involved between the set point and the process variable. The units can be a little bit tricky because different manufacturers might use different units when you're changing the setting or the factor associated with this P. So one example might be the controller output, so whatever electrical signal is being sent out, say 0 to 10 volts, over the throttling range, or what the input or the sensor data that's being delivered to that controller is. You could look at that controller output in terms of percentage, you could look at just the throttling range, or you could look at the throttling range in something called sensor span. Now, we don't need to be experts about all these definitions and readily recognize exactly what we're saying, but it's important to recognize that some of these units may be in terms of gains, meaning the larger that you make that P value, the more magnitude of response you're going to give your system from that P variable. And some of these are inverse gains. With the way that those different units are rearranged, we can make a bigger value have less response from our P factor. Let's do a quick example to see what that looks like. So for the first set of units that we had there, that P value being the full output range of the controller over the controller throttling range. So again here, the output range could be a electrical signal going out to something like a coil valve, and then the throttling range is the amount of change that we want to have at the controller input to cause the controller output to go to 100%, whatever that may be. So for that same coil application, this may be some reasonable numbers that we start with. So if we have a 0 to 10 volt output from the controller to the valve, we might have a 10-degree throttling range, which means that, say that we want 55 degrees set point at our coil discharge. Well, when we get to 60 degrees, that's telling our valve that we want it to go to 100% of its controller output, assuming a calibration point. Or what we're really saying with this P setting is that for every degree off we are from set point, we want to have a 1 volt response going to our valve. So let's see what that looks like. So if we have this time series chart where we can look at the controller output on the top, so the 0 to 10 volt that could be going to the valve, and let's say this had a calibration point or a starting point of 5 volts. So that's its error-free mode that it starts in. And let's say on the bottom we're looking at the coil discharge air temperature in degrees Fahrenheit. So that 55 degrees is the set point that we want to be at, and we've just introduced an error. So let's see what that looks like. So we can see here that we have that magnitude response, that when we get 1 degree off of set point, we're seeing a 1 volt change in our controller output. When we get all the way to the edge of our throttling range, so at this 60 degrees Fahrenheit at our coil discharge, now our controller output is going to, for proportional control, sit right at 10 volts until you get back within that throttling range. So we see here we have some overshoot, and we see that at the end we're stuck with a little bit of steady state error. So one of the disadvantages is that you have that steady state, and depending on how you set your P, you're going to have small errors that you're going to be stuck with. So the magnitude of that error can be changed by changing your gain and the sensitivity of the system. When you have low sensitivity, that's essentially going to be resulting in low steady state error. But when you have high sensitivity, that could result in overshooting your system and being stuck with more of that steady state error. And when we make changes, as we'll see, one of the common practices, rather than make incremental changes to the proportional value, you may have or double that setting so you can really see how you're affecting the control response in your system. So what do we get with proportional integral control, or PI control? Well, we can get rid of that steady state error, and that's because with the integral component, it's constantly summing up or accumulating the error over time. So even if you have a small error, it's going to adjust the magnitude of the control response until that error goes to 0. It's also advantageous because our control systems change, and the disturbances and the noises and the infrastructure involved can all have an effect. So if you have a system tuned one way at its commission state, that may change over time, and having the integral being able to account for the time component of its control response can be a benefit. But the disadvantage is that with too much integral, you might have a slow response versus what you had with a proportional only. It's a slight disadvantage because, as we said, with HVAC processes, we're usually okay to be slow, and we have a fair amount of tolerance there. And again, just like proportional, as we're tuning these things, it's appropriate to do things like halve or double the setting to see if that's giving you a meaningful change in your response. So let's look at what it looks like on this time series when we add in that integral. So this would have been the same response here, and we can see a few things. Is that one, we're avoiding the overshoot that we had with proportional, so we have a tighter control loop. And two, we eliminate that steady state error. And again, that's because it's caring about how long it's been off from set point to adjust the magnitude of the response. So what do those units look like? Well, again, you can have things inversed here a little bit. So I'm showing units of seconds per repeat. You can also have units in repeats per second. But in the way that I have it here, we can change the I value, or the integral component and its setting, to something like 30 seconds per repeat, which means that it's going to sum up all the error and it's going to repeat that summation in 30-second intervals. Compare that to something like a slower 120 seconds per repeat, and we can understand this in terms of high and low gain. So the faster that we repeat those cycles of accumulation, the better or faster response that we're going to have in our system. So we won't say much about derivative control. So as we said, that while helpful for a process where you have really quick changing variables, that's not going to be most of our HVAC systems in commercial type buildings. So it's very helpful because it can project when you're about to overshoot, but that little bit of helpfulness that we get and that added control robustness is often not worth the complexity in tuning and what can go wrong if that desetting is messed up or does not apply to a different application or a change down the road. So a few things to remember. First is that controllers really need to be tuned. So you may hear things like a factory tuned controller is good to go out of the box, but one thing that we want to stress is that you have these systems of lags. So if you have something like a pipe sensor probe that's in a well, that's in a piece of pipe, you can imagine that there's a certain thermal lag associated with how well that was done that you want your control system to be tuned to handle, so that it's not constantly overshooting or cycling or not accounting for that specific set of lags in your system. And also that this has to be done safely. So one of the things that you may want to keep in mind with things like pressure and temperature, as you're introducing some new loop or trying to tune things, you want to make sure that there's safeties in place that will protect the equipment if you do have something like overshoot as you're tuning or when you're done with the loop. So an example would be putting in something like a duct static pressure reset sequence. So the way that that may be adjusting your set point, you may be throwing your fan speed around in a way that you may see a very instantaneous high gain in your duct. And you want to make sure there's some protection equipment like a discharge high limit pressure switch that will turn your system off so that if you get to that high overshoot, you can make sure you're not going to blow up any duct in the process. So check that a switch like that is there, and test it to make sure it works before you do things like play with the settings. But I will say from experience that when you have good resources like something like a field manual here, and when you've done your due diligence, coordinated with O&M folks, made sure that those safety devices were in place, that this can be a very doable and fulfilling process to go through a loop and do this tuning. And just to give a quick kind of how-to guide of what that looks like, it's a process that looks something like this when you follow these types of field guides. You may start by turning off your I&D settings as a start. You'll reduce your P gain, or you'll start with a very low P so that you have a slow response. So once you see that you have that slow response in your system, you start multiplying the P gain by 2 repetitively until you see that you've had some set point change that you can register at a reasonable time. You continue doing that until you start seeing the beginnings of cycling, or that sinusoidal response and feedback in your system. Keep making P change until you accomplish what looks like a perfect sine wave, so perfect cycling. It's not something you want actually in your system, but in this tuning process, once you have that, you can divide by 2, because you've now found a good magnitude that you can back off from, and you can fill in the gaps with this integral gain. So now you've reduced the integral gain by 2, divide by half, until you see that you've limited your overshoot, and that in a reasonable amount of time you can get to effectively 0 steady state error. So that's what the process looks like. So as a recap, we looked at a little bit about how the industry has moved from pneumatic to DDC. We've looked at about how control loops from a theory standpoint haven't changed, and that we're still dealing with in HVAC a lot of closed control loops where we have feedback, comparing that to a set point, and having a magnitude change at the output of our controller. We looked briefly at what some of the simple schemes like 2-position and floating control look like, and then we looked at some examples and some theory behind PID loops.